Okay.
Wonderful. Okay, now, yesterday, and this is where it's handy to kind of look at the big picture in terms of like how these vectors work, and just because you can use a calculator doesn't mean that you have to then like completely abandon any idea of like making a sketch to see how this thing is going to play out. So, kind of got through the beginnings of number 4. So like at number 4, you want to figure out what the x and y components are. Now, let me show you kind of different ways to do, like if you have vector c on number 4, which is 4.76 meters per second squared at 195 degrees. So if you just make a sketch of that vector c, which is down here like 4.76 meters per second squared, and that's at 195 degrees, okay? Now, there's a couple of things that you need to look at. How I approach this problem was probably different than how you all approach the problem. Because of the fact that, like we talked about yesterday, when I learned how to do this table only went up through 90 degrees. I could not look up the sine, cosine, tangent, whatever, of 195 degrees. It did not exist in the table. But what could I look up? Now,
Minus
keep in
180.
mind, I'm trying to find this x component and that y component. 195 degrees gets me all the way to here. So what would be this angle in here?
15.
15 degrees. Now, what I could look up is the sine, cosine, tangent of 15 degrees. But I couldn't look up 195 degrees. Now, so how and again, you just become a creature of habit. Even on a problem like this, for me it's difficult to realize, well, if I take the sine of 195 degrees and multiply that by 4.76 meters per second squared, personally it's a little bit for me to realize, to visualize the idea that this gets me the side opposite of 195 degrees. Because if you think about it, the side opposite of 195 degrees visually means that it's like somewhere up in here in terms of the side opposite. But if I just work off of the 15 degree angle in here, that makes this easier to see. Oh yeah, 15 degrees, here's going to be the side opposite. That's something for me that's easier to visualize. Okay? And the same thing getting that x component using that 15 degrees. No matter how you do this, okay, but here's the end result. And this is why it's handy to make a simple sketch. When you get done at the end of the day, when you're finding these x and y components, because it's in the third quadrant, what do you know about the sign of your x and y components? They're both negative, okay? They're both negative. So this is why it's handy to make this sketch. So that you, and some God forbid your calculator just might lie to you, but that way you know that you get this. So what I would do, again, if I were doing this, I'd take the sine of 15 times 4.76. I'd just get those numbers, and then I'd put negative signs on them. Okay? That's just because that's just how I grew up learning how to do these problems. 195 degrees was not an option. Okay? It really wasn't. It just wasn't there. So, now, if you look down on number 5, let me give you some hints on some of these on number 5. And again, sometimes it's handy just to make a sketch so that you know where you're going to end up. So in number 5, you want to add vector B to vector E. So, and all I'm going to do is I'm just going to make a sketch of this. Okay? I got vector B 5.75 at 90 degrees. Okay? So here's vector B. 5.75 degrees at 90 degrees. I'm just going to make a sketch. I'm not drawing this to scale. I just want to get an idea of where I'm going to end up. Now, vector E is 8.78 at 110, right? So how am I going to draw vector E from this at 110 degrees? Roughly where's it going to go? Mr. Baker gives the international sign for up and to the left. Okay? So it's going to go something up like here. So here's vector E, right? True? So when I draw, here's vector B, here's vector E. So when I draw that resultant, okay, just based off a simple sketch, just based off a sketch, what do I know my angle, my resultant angle has to be greater than? 90. And it has to be less than 180. So right away, just based upon this sketch, I know that if I get an angle that's not between 90 and 180, I've done something wrong. Okay? Now, Hayden came in before school and he says, hey, do we have to draw these charts? Categorically, without fail, yes. I want to clearly see what you've added, the sum of the x components and the sum of the y components. So, like on that one where you have b plus e, okay, let me make sure everybody's got these numbers. So when you add b and e, your x component should be -3, because that's the only x component that there is, and your y component should be like 14. Okay? And you add those together. Your x components on that one with b plus e, your x components should add up to -3, and your y components should add up to 14. Now, here's the significance of this. So when you get those columns, and you draw these columns, and you find those sums of your x and y components, and this is going to be -3, and this is going to be 14. That's half the battle. Okay? That is just half the battle. Then it's like, well, what do we do with those? Okay? That's the next step. This is why it's vital that you make a simple sketch to see where you're going to end up. You're going to go, okay, and you always draw that x component first. So I'm going to come over here at -3, and then I'm going to go up 14, and then I'm going to draw that result. Now, this is where your calculator, thank you, will lie to you. Okay? Your calculator lies to you. You go, we're besties. Yes, your calculator completely rolls you under the table. Because if you trying to find this angle, okay? That's what you're trying to find. If you punch into your calculator the inverse tangent of 14 over -3, what does it tell you the angle is? Somebody do that. Punch in the inverse tangent of 14 over -3. Courtney, what do you get? Negative what? 77.9. -77.9 degrees. That's what your calculator tells you the angle is. Your calculator lies. First off, can any angle in this system be negative? No. That dog will not hunt. So you cannot have a negative angle. Under any circumstances, can you have a negative angle? You can have negative x, you can have negative y, positive x. But you cannot ever have a negative angle. But this is why it's handy to make a sketch. So your calculator says this is -77.9. Now, if it were me, okay, if it were me, this is what I would do. I wouldn't even punch in that negative sign. Literally, I would not even punch in that negative sign. I would just do the inverse tangent of 14 over 3. And I would just find this angle. Okay, that's all I would do. I would just find this angle. I would not even worry about the negative sign. I just do the inverse tangent of 14 over 3. But then, what would I do? Because what's the ultimate angle that I need? Measured from where, Sydney? Yeah, I need it from this positive x-axis coming around here like this. So when I get this angle, what can I do to get what's ever left over? Subtract it from 180. Okay? So if all goes well on that B plus E, your angle should be a country music radio station in Wichita. And if you don't listen to country music, then you don't get the hint.
Do we add the decimal?
Isn't it like 102 or something?
You can or you can't. It's up to
Yeah,
you.
102.1.
So we have to worry about single figures and this?
Oh, you do.
I don't
You
listen
do.
to country
But
music.
technically,
Country
this
music is like
has
the
3
death.
significant digits. Okay? So then when you add that to 180, then because you're adding, you would keep keep that tens place.
Okay.
Is that 85.1? 95.
Now, on number 5, when you do C plus F, okay, if all goes well on that angle on C plus F, you should have an angle between 200 and 220 degrees.
So you're gonna do this, right?
Yeah, I'll show you.
On number 6,
We'll do it there.
So we could turn
the angle should be between 70 and 80 degrees. And on number 7, the angle should be between 170 and 180 degrees. Riley, we doing okay?
Yeah.
Love and life.
down about 6 minutes
Fantastic. That's what I need to hear.
for trouble.
Okay, now, since the test is tomorrow, and I promise you, you're going to have to do problems like this on the test. Okay, I promise you. Hello, didn't mean to drop that. If you want to hold on to this, hand it in tomorrow, you can. If you're done with it and you're feeling good about it and you want to hand it in, that's cool too. Okay, so you can hand it in today, hand it in tomorrow, whatever works for you. Okay, read.
Your tests build on each other. Like,
Well, just by their nature. I mean, yeah, they
Better go
do,
to
but it's
bed
just
early tonight.
the nature of how physics plays out.
No, it's better than 11.
I mean,
I sent mine tomorrow.
you're going to be doing velocity calculations tomorrow that are going to end up in meters per second. So that's kind of what we talked about the very first day. So,
1:30 in the morning?
yeah.
And I wasn't even
They
doing
did.
anything. I was sitting staring at a wall.
We're good?
Pretty much. Yeah.
Courtney?
Are we allowed to either way of doing this? Are we allowed to do?
On the test tomorrow, while we're talking about this, okay, here, you're going to have 3 problems involving vectors. And I'll tell you exactly what these 3 problems are going to be. The first problem, I'm going to give you an individual vector, and I'm going to say, no, this will be the second problem. No, I take that back. The first problem, let me give it to you in sequence. The first vector problem you have, I'm going to give you like 3 or 4 vectors. And I'm going to tell you explicitly to draw them out using a protractor and ruler. Okay, and then you find the resultant that way. Okay, so you will explicitly be told, here's protractor, here's the ruler, this is how you can find the resultant. Okay, categorical. The second problem you're going to have is that I'm just going to give you an individual vector, and I'm going to tell you, use trig functions to find the x and y components. Okay, that's all you have to do. Now, if you want to make a sketch of that to see what's going to happen, but at the end of the day, how you're going to find the x and y components is you're going to use a calculator. Okay, sine and cosine. The third problem you're going to have is something like this. I'm going to give you 2 different vectors, and I'm going to say, find the resultant. And again, you are more than welcome and actually encouraged to make a sketch of what's going to happen. But at the end of the day, and listen to me on the test, at the end of the day, I see this chart. If I don't see this chart, even if you have the right answer, you will not receive full credit. Okay? So, the first one, categorically, you use the protractor ruler. Second 2, you use trig functions. But that doesn't mean you can't make a sketch. We're good? Beautiful? Fantastic.
Will we ever get to
All right.
I hope not.
So, no more questions on that sheet? All right, so let me hand out kind of the review of what's going to be on the test, and then we'll carry on.
Good.
All right, so let me kind of go through the things that are going to be on here. First off, let's start with the basics. Vector quantities, scalar quantities. At the end of the day, what is the difference between the 2 of them, Danny?
Scalar just has like a number, and then vector has stretching and magnitude.
Fantastic. Okay? That's the fundamental difference. The only what they have in common is that they both have a number or a magnitude. The difference is that one of them has a direction. Courtney Lang, give me an example of a vector quantity.
You are
traveling at a certain speed in a certain direction, that's it. If that makes sense. I don't know what you're looking for.
Otherwise, what you just described is velocity, right? Bless you. So velocity is just speed with the direction. So if Courtney just says, hey, you know, she sends a text and says, hey, I'm driving 50 miles an hour. That just is the magnitude. Okay? So I don't know which direction she's going. I just know that she's going 50 miles an hour. Now, if she says, I'm going east at 50 miles an hour, then that becomes a vector quantity, because then I know the magnitude, I know how fast she's going, but then I know the direction that she's traveling in. Okay? So, velocity, forces, acceleration, displacement, all of those are vector quantities. So what's an example of a scalar quantity? Mr. Moon?
Mass.
Mass. Okay? If I just have a mass of 1 kilogram, it doesn't make any sense to say, oh, I have a mass of 1 kilogram east. Okay? Just 1 kilogram. Okay? Energy is another one that's a scalar quantity. Okay? If Reed says, oh, I got a lot of energy. Okay. Cool. Okay? It isn't like, I have a lot of energy going north. All right? It's just, I have energy. So, basically, if you can draw it with an arrow, it's a vector quantity. That's kind of the simple rule. Okay. Frame of reference. What does frame of reference refer to? Riley J.
Like, if you're just talking about like this room or like the universe or...
It's basically, you're right. It's how big is the picture. Okay? Are you talking about moving within this room? Or are you talking about the Earth spinning on its axis? Or are you talking about our Milky Way galaxy being drugged through an expanding universe? Okay? Just how big a picture are you looking at? That's the short version works. Reference point. Can the reference point be a point that is moving? No. Okay, your reference point is going to be a fixed point. That's going to be arbitrary. Okay? Your reference point might be at the beginning. Your reference point might be where you end up. Your reference point might be in the middle. So your reference point is a completely arbitrary point. Okay? That's it. So then you've got position. Now, could position be a negative value? Give me an example, Riley J.
If you were going to the left of your reference point and that was the negative side.
Okay? So let's say that here's basically, you can think of like frame of reference as kind of like being in a number line. So let's say you make this the reference point. And typically your reference point is defined as being 0. It doesn't have to be, typically it is. So then you might have like 5 meters, 10 meters, 15. And then you'd have negative 5, and then you'd have negative 10, whatever. So your position is just where you're at. Could be negative 5, could be positive 5, could be negative 10. Okay? It is where you're at that particular time. Now, if your position changes, what is that called? What is that change in position called? Sydney? Displacement. Wonderful. And how do you, there's a couple of different ways you can calculate displacement. If you know the two positions, how can you calculate the displacement?
Is it initial minus final?
It is. It's, well, flip that.
Final minus.
It's always final minus initial. So let's say that I am here, okay, at an initial position of negative 5. I stroll casually over here to 10 meters, okay? So, Elijah, how can I calculate my displacement?
Initial at negative 5, minus 2, final.
So, is the naught value, x naught, is that my initial or is that my final position?
What's your final, your initial?
So, in this case, x naught would equal negative 5. My final position is going to be 10. So x is going to equal 10. So my displacement would be Final minus initial, right?
Squiggly.
So you're going to take 10 minus what? Negative 5, and you're going to get 15. Now, here's what you're going to do wrong. Mark my words. This is what you're going to do wrong. And you sit there and go, oh, we won't do that, Mr. Marquette. Yes, you will. You're going to look at 10, and you're going to say, and you're going to see negative 5 and go, oh, my displacement is 5 meters. Because 10 minus 5 is 5. What's the big deal? Why is this so difficult? No. No, no, no. Now, is that information enough to give me a velocity? Mr. Baker, can I get my velocity from that?
No,
What else do I need?
no time.
I need my time. So, sounds like a commercial. I need my time. Okay? So let's say my time is 3 seconds. It took me 3 seconds to do that, assuming that I'm moving at a constant speed the entire time. So what's going to be my velocity? Paige,
5 meters per second.
how'd you get that?
13 divided by 4.
Fantastic. So Paige said, hey, look, velocity is my displacement divided by time. In this case, that's going to be 15 meters divided by 3 seconds. I'm going to get 5 meters per second. Hey, pretty good clip. Now, remember, velocity is a rate of change in position. Okay? Now, did I go past the reference point? Yes. Why didn't my velocity change sign because I went past 0 meters? What would you say, Gregor?
Because you're still traveling in the same direction.
That's true. Just because I'm still traveling in the same direction. The fact that I went past the reference point, does that have any bearing at all on my velocity? No. I could have started out here and stayed in the negative region and still had a positive velocity. So here's the question. Does a positive velocity always indicate that you are going towards the reference point? No. Okay? I could have a positive velocity and be moving away from the reference point. I could have a positive velocity moving towards it. Okay? So get out of your minds right now that you can just look at the sign of velocity and figure out where you are in terms of the reference point. The only thing you can tell is which direction that you're traveling. You cannot tell where you are in relation to the reference point just based upon the sign of the velocity. Okay? Good with this. Now, what's another way that I could represent this motion? That I started at negative 5, I ended up at 10, and that took me 3 seconds. How else could I represent that exact same motion? Garrett.
On a position time graph.
Oh, I can draw a position time graph. So Garrett, what would my position time graph look like? Fine.
It'd just be a constant velocity, right?
Where would I start?
0.
No.
Was
there
it
might
negative?
be
It
a
was.
zero line, don't get me wrong.
It was. Was it negative 5?
Well, let's go back. Oh,
Remember?
where did I start?
Negative 5 meters.
Where did I end up?
10.
10. So I'm going to start down here at
Negative 5.
negative 5. I'm going to end up here, there's 5, there's 10. There's 1 second, there's 2 seconds, there's 3 seconds. So what's it going to look like?
Just a straight line.
International sign for a straight sloping line, either that or you're the Pope and you're giving a blessing. So let's go with it. This is a position time graph. So we got this action going on, right? So at 1 second, where was I? David, where was I?
0.
Was I changing direction since I went through 0?
No.
Why not?
You're going this direction because you recognize that, but you're going towards one direction.
It's true. But would you agree at the 1 second mark, I am at the reference point?
It's just
Yes. But Why didn't I change direction? What do you have to change on a position time graph to show a change in direction?
Slow down, stop, speed up.
3 things. Slow down, stop, speed up, right? Am I doing any of these 3 things by showing this on a position time graph? Am I showing slowing down? Hayden, why not?
Because it's just a straight sloping line. Your
And
velocity
the, and the
is the same.
slope of a position time graph represents what? Velocity. Well, kind of direction, but let's just go with velocity, right? So, the only thing that you can tell is where I'm at as a function of time. Now, David had a very good point. I didn't change direction. Even though I did go through 0, I didn't change direction because I still have the exact same slope, okay? I'm just moving with the same speed all the time and in the same direction because it has the same slope, okay? Now, could I find this area right there? Could I find that area, and would it have any meaning whatsoever? Reed, you shake your head emphatically no.
No,
Why?
because it's a position time graph.
It is a position time
We only
graph.
do that with
But so what?
We only do that with velocity time graph.
Why?
It's on a position time graph, the slope represents velocity.
That's true, but I'm not talking about the slope. I'm talking about finding that area.
You already know your distance traveled.
Why?
It's position time graph, position, distance. Right there.
Okay? Now, what Reed is saying, and very emphatically too, okay, even kind of a little bit of this action going on, is the fact that it's very easy to find out how far I went because I know my final position is 10, I know my initial position is -5, okay? That's how I'm going to figure out how far I went. I went 15 meters. I went 5, 10, 15. I don't need the area to tell me my displacement. I just figure out the change in my position. Now, let's say that you get confused. Okay? It's the throes of the test. You have a small momentary lapse of judgment. You go, oh, I can find the area. Now, let's just play the units game. Let's just play the units game. If I were to find this area, what would I multiply together? What 2 physical quantities would I multiply together?
Meters times seconds.
Meters times seconds. I would have some number of meters times some number of seconds. What units do I get when I multiply meters times seconds?
Meter seconds.
I get meter seconds. What, pray tell, is measured in meter seconds? Butkus. Okay? It has absolutely no meaning whatsoever. This area, if you found it, I don't know why, as soon as you looked at the units, you would go, well, that was stupid. Nothing's measured in meter seconds. Okay? Won't work. Right? Now, how can I show, at the end of 3 seconds, I want to come to a rest. I want to stop. I don't want to get arrested. I want to stop. Okay? Which would probably be arrested too. But let's say I want to stop. So what can I do? Okay? Y'all are doing the international sign for a horizontal line, meaning that I'm at rest. Right?
International.
So this is going to plateau out something like this. Now, does this show me slowing down?
Yes,
Yes. Why, Riley?
because it curves to a stop.
That's right. By tangent lines, right, we're going to come through like this. Now, let's talk about tangent lines. I promise you tomorrow, 2 things are going to happen on the test tomorrow. The sun's going to rise in the east, okay, and you're going to have to draw a tangent line on a position time graph, okay? Those are the 2 things that I promise will happen tomorrow. If for whatever reason the sun doesn't come up, like if the sun's gone out overnight, we won't have the test because we're going to have other issues, okay? But assuming that the sun does rise in the east, it doesn't rise, we just spin and then we see it, okay? That you're going to draw a tangent line on a position time graph. If you get done with the test tomorrow and you hand it in and you have not drawn a tangent line and found a slope, something has gone wrong. Okay? Something has gone wrong. So, little self-check tomorrow when you hand it in. Ask yourself, Gee, if I draw on a tangent line. If your answer is no, whoa, something's gone wrong. I promise you, you're going to draw a tangent line. Now, would I ask you to draw, why would you scoff at me? And if I said, hey, I want you to draw a tangent line at 2 seconds. Why would you all go, oh, Burkamp, that old age thing isn't working for you, man? You know? Why would I not ask you to draw a tangent line at 2 seconds? Could you physically draw a tangent line at 2 seconds? You couldn't draw a tangent line at 2 seconds if you tried. Okay, well, how would you draw it? Right angles? That doesn't make any sense. Okay? Why would I not ask you to draw a tangent line at 2 seconds? You already know the velocity. And is the velocity changing? No, because what's the only time you need to draw a tangent line on a position time graph? To find instantaneous velocity. Well, can you find the instantaneous velocity at 2 seconds? Is it going to be the same at 1 second? Is my instantaneous velocity at 2 seconds the same as my velocity at 1 second? Yes, why?
It's still going the same velocity.
How do you know?
Slope.
Slope is still the same. So, it would do no good to ask you to draw a tangent line if the velocity is constant, otherwise known as this constant slope. Now, I could come up here and say, okay, a little past 3 seconds, I want to know what the velocity is just a little past 3 seconds. So, I could come in here and draw a tangent line like this. Now, just based upon this visual, okay, and just based upon this visual right here, is my velocity at this point faster or slower than what it is at that point? Why?
Because once it reaches the peak, it's going to go zero. Or change direction, sorry. When it changes direction, it becomes zero.
We got nothing about changing directions. And pretend that you're in a math class. Okay? Is the slope of this line bigger or smaller than the slope right here? Smaller, right? Line is flatter, so the slope is, yeah, because when you get a horizontal line, what's the slope of a horizontal line? Zero, right? So this line, the slope of this line is approaching zero, which means my velocity is approaching zero. So that means that I am slowing down. So just if you were just look at this slope of this tangent line right here, and compare it to this, you'd go, hey, I got to be going slower because my slope is a little bit less. Okay? Now, I can find a point. So I would give you on the test, this is exactly what I'm going to do. I'm going to give you a specific point in time. And I'm going to say, find the velocity at this point in time. You're going to draw a tangent line. Now, just drawing the tangent line is only half the battle. How are you going to use the tangent line itself to find the instantaneous velocity? Hayden?
By taking 2 points and finding the slope.
Now, listen to what Hayden said. Said you have to take 2 points on the graph.
Or on the tangent line.
On the tangent
Okay,
line.
yeah.
Okay? So, you would have to pick physically, whoa, that didn't work. Let's try this. You would have to physically pick 2 points that are on the actual line to find the slope. You cannot just take that position divided by that amount of time and say that's my velocity. You would physically have to take and divide that out. Find the 2 points, find the slope, that's going to get you the velocity. Now, let's say this goes out to 4 seconds. I want you to find the average velocity in the first 4 seconds. I want you to find the average velocity in the first 4 seconds. What 2 things would you need? One rhymes with displacement, and the other one rhymes with rhyme. Time. Okay? So, And you all have done this calculation, okay, on that constant velocity lab, right? How did you calculate, bless you, how did you calculate your average velocity? What did you need? No, not distance, displacement. And you needed time, right? So, what's my total displacement during this time interval?
15.
My total displacement would be 15 meters, right?
Yes.
Which would be position final minus position initial. So my total displacement would be 15 meters. And I'm going to divide that by however much time it took, which is going to be 4 seconds. So I'm going to take 15 and divide it by 4, whatever I get, boom. That's my average velocity for that interval. So don't confuse instantaneous velocity with average velocity. Okay, they're both measured in meters per second, but they're going to represent different things. Now, at this point, I'm going to take this curve, I'm going to take it up, and then I'm going to take it down. What's happening up here? How do you know it's going to change direction? How do you know that it slows down, stops, and speeds up? There's a curve. Now, a couple of things that I heard that are good and a couple of things that I heard that are a little sketchy. Okay? If I ask you, how do you know that an object changes direction on a position time graph? Okay? Do not tell me, oh, the slope changes. Why is that not enough information to tell me that you're actually going to change direction? If you just tell me the slope changes, why is that not good enough?
Because that could mean just speeding up or slowing down.
Yeah, look, at this point right here, is the slope changing?
Yes.
But did I change the direction? No. Now, if you tell me the slope changes sign, that's enough information. So at this point, does the slope change sign? Yes. Now you're okay. Okay? Now, here's the other thing. Something that Graeber said. There's 3 things that have to happen. Slows down, stops, changes, and then speeds back up. If it's a curve like this, and if you come up here at the top and you draw that tangent line is going to tell you at that instant the velocity is 0. Okay? Which means that's when you're going to change that direction. Is when you reach that point up here. Okay? Now, just because your velocity goes to 0, does that mean that you're going to change the direction? No. Yeah, you could be driving down the road and you hit a stop sign and you not physically hit, but you encounter a stop sign. Okay? Don't hit the stop sign. Okay? You encounter a stop sign. Okay? And you all being teenagers who follow the rule of law in traffic to a T, you physically come to a stop, okay? Don't just coast through it, okay? You slightly tap on pedal, you don't think that's what the stop sign means. So, you actually come to a stop, look both ways, and then proceed, all right? So, you came to a stop, but that doesn't mean that you changed direction. Now, if you really wanted to be safe, how could you always guarantee that you actually stop at a stop sign?
Shut your engine off.
Huh?
Shut your engine off.
No. Beyond that. How could you make sure that you actually came to a stop at a stop sign?
Come to 0. Put it in park.
But beyond that.
Go more forward.
No. Look at this. What did you do?
You go in reverse.
Change direction. Okay? Pull up, back up a little bit, and then go forward. Okay? You'd actually stop twice because you'd have to stop, just put it in reverse, and then have to stop again to put it in forward. Okay?
All right, I'm gonna do that for
Now that's a bit over the top. Okay?
You're going to do that from now.
Shutting off the engine is a little bit over the top. Putting it in park, okay, hey, maybe that's it. So, okay.
It's a long light.
So we're good. Now, if I were to ask, let's say that this point in time out here is 10 seconds. If I ask you to calculate the average velocity for this graph, what would it be? How would you even start? How could you calculate the average velocity for this big monstrosity? What's your final position?
0.
It's like 1.
What's my initial position?
5.
So what's my displacement?
5.
5, and then I would divide that by 10, and I would end up with half meter per second. Okay? So even if you have this big monstrosity, dips and doos, doesn't make any difference. It's all, your average velocity is always going to find the minus initial. Got it? Good? Grand? Beautiful.
Fantastic.
Now, what's another way that I could represent this constant velocity of 5 meters per second? What's another way that I could represent that constant velocity? A velocity time graph. Daniel's giving the international sign for this. Right?
Time graph.
So let's talk velocity time graphs. So here's 5 meters per second, right? There's 3 seconds. So does this show constant velocity? Elijah, why? Which indicates what? What's my acceleration? 0. Now, on the test, do not get, and I'm going to tell you this on the instructions on the test. If I'm talking about an acceleration, I'm talking about a non-zero value of acceleration. Okay? So don't tell me, oh, I can travel at constant velocity and still have an acceleration as long as that acceleration is 0. No. No. Okay? If you have no money in your account, you are broke. Okay? If there's no acceleration, there is no acceleration. Don't tell me, oh, you can have constant velocity and accelerate as long as the acceleration is 0. No. That's like saying I have no money in my account, but I'm going to go and buy a pizza. No. It won't work. So, you can have a constant velocity, okay, but then there is no acceleration. Remember, every motion that we will study is going to be one of two things. It's either going to have constant velocity and you're going to have no acceleration, or your velocity is going to change and there is going to be acceleration. Those are the only 2 games in town. Okay, that's it. You're not, oh, I'm kind of accelerating. No, you're really not. Okay? You're either accelerating or you're not. Now, could I find that area? Yes. And what would that area represent? Displacement. And if I took 5 meters per second times 3 seconds, then I would get 15 meters. Now, just based upon this, can you tell with this displacement of 15 meters where you are in relation to the reference point? The only thing you know is the displacement is 15 meters. Just based upon this number, you cannot tell that you went from -5 to 10. You could have gone from 0 to 15. You could have gone from 1,015 to 1,030. Doesn't make any difference. The only thing you know is that you've traveled 15 meters. That's it. Okay? Where you are in relation to the reference point, you cannot tell. The only thing you've known is that you've gone 15 meters. Now, I'm going to add to this line. We're going to bring this up, down, like this. So I've got this line coming up, steep, something like this. Now, let's assume these 2 lines are parallel. Okay? Try to draw them parallel. When you have 2 parallel lines on a velocity time graph, Mr. Baker, what do you think that would indicate?
They have the same acceleration.
They have the same acceleration, right? As long as these 2 lines are parallel, that means I have the same acceleration. Does that mean because the 2 lines are parallel, does that indicate that in both situations I'm either speeding up or slowing down? Because the 2 lines are parallel.
Well, it shows acceleration, so
This is true.
yeah.
Yes? Everybody cool with that? If you have 2 parallel lines on a velocity time graph, that means they're both going to show the same event happening, both speeding up or both slowing down.
No,
You all cool with that?
no.
Don't be. Do not be cool with this in any way, shape, or form. From here to here, am I accelerating?
No.
Yes.
Paige, why did you look with, and you should, why did you look at discuss with Riley when he said, no, we're not accelerating?
Because you are.
Okay.
That's a legitimate answer. Test is only tomorrow.
Paige, how do you know you're accelerating?
Because the top one, well, it has a positive slope.
It's true. It does have a, I'm not denying that. It does have a positive slope. Okay? Is your slope a non-zero value? So therefore you are
Accelerate.
accelerating. Is this acceleration making me speed up or slow down?
Speed up.
How do you know?
Because it has a positive velocity and a positive acceleration.
Oh, brilliant. This has a positive slope, which means I have a positive acceleration. I also have a positive velocity, therefore I am speeding up. Okay? Brilliant. Now, what's another way that you can just look at the graph and figure out that you're speeding up? Rosie, how can I just look at this graph and know that I'm speeding up from here to here? We've already established that. What does this line represent right here? Let me give you a hint. It rhymes with 0 meters per second.
0 meters per second.
0 meters per second. Okay? So am I going away from 0 meters per second? Which means that I'm doing what? Either speeding up or slowing down. Speeding up. So if you look at this line, okay, if you look at any velocity time graph, any line on a position time graph has one of three options. It's either parallel with 0 meters per second, which means what? Constant velocity. It's either going away from 0 meters per second, which means you're speeding up, or it's going towards 0 meters per second, which means you are slowing down. Those are the only three games in town, people. That's it. You're either speeding up, you're slowing down, or you're at a constant velocity. That's it, nothing else. Okay? There is nothing else. There is no choice D, all of the above. No, it's going to be one of those three things. So, one way you can figure out is the fact that you have positive acceleration, positive velocity, and I'm speeding up. But it's going away from 0 meters per second, also indicating that I'm speeding up. Now, at the very top up there, listen to me very carefully. At the very top up there, when it peaks over, relative maximum for you math nerds. Sydney, did I change the direction at that relative maximum up there? No. You're right. Why are you right? Why didn't I change the direction? It breaks over and changes.
Because this is the problem between that and position time graph. When moving, when going over, you're either accelerating by speeding up or slowing down. And by going over, you're switching to slowing down, not changing direction.
Beautiful explanation. Spot on, beautiful explanation. Okay? So what she said is that I went from speeding up, okay, because I'm going away from 0 meters per second, and then I'm going to start slowing down. But I'm still going in the same direction. Why? What has not changed? I have not crossed the 0 meters per second line. Okay? Now, am I slowing down?
Yeah.
But I'm still going in the same direction. So true or false, if the slope of a velocity time graph changes sign, the object changes direction. Categorically false. Here's the classic example right here. Now if I said, true or false, the slope of a position time graph changes sign, the object changes direction. That would be true. Okay? That would be true. Keep those two straight. Now, from here to here I'm speeding up. From here to here I'm doing what? Slowing down. Now, at this point right here, where it crosses the 0 meter per second line, Danny, did I change direction?
Yes.
Yes. Does this meet the 3 criteria needed to change direction?
Yes.
Why?
It slows down,
Okay.
slows and speeds up.
Bingo. I slow down, I go to 0, then I speed up. Now, if on the test I give you a graph like this and I ask you to indicate when it's speeding up or slowing down, don't look at this and go, oh, it slows down this entire time. Okay, that's the most common thing that you all do wrong. And on that assignment that you all did, assignment 2-1, a lot of you did that. I slowed down till I hit 0. Once I cross 0, then I speed up. I'm not slowing down the entire time. I'm only slowing down till I hit 0, then I begin to speed up. Now, visually, just on a visual thing, let's say that I give you a different velocity time graph, okay? And one is kind of coming down like this, and then it goes like this, okay? And then maybe something like that. So let's say this is a velocity time graph. Here's 0 meters per second. Positive, negative. If I just gave you that graph without any numbers at all, how could you visually look at that graph and find the region of maximum acceleration?
The biggest slope.
Yeah, the steepest slope, right? Because remember, what is acceleration?
So
Well, it is the slope.
Change in.
It's the rate, okay, listen to me, a rate of change in your velocity. It's a change in velocity per unit of time. So, anytime you have a big change in velocity in a small period of time, that's going to be your maximum acceleration. Now, I want to give you 3 options. Here, so here's A, here's B, and then you have C, which is the entire time. If I gave you those 3 choices, A, B, and C, A is the first half, B is the second half, and C is the entire region. In which region, A, B, or C, is their maximum acceleration? How many vote A? Reed, come on, be Jayhawk, stand proud.
Brad said that.
Oh, no. Okay, way to be Jayhawk. All right, so to speak. All right, how many vote B? 1, 2. Okay, how many vote C? Some of you didn't vote, but most of you voted C. I love America. Veterans died so you could go. Okay. Now, do you have a better reason for voting A other than Brett said so? Why?
That's the biggest, goes the longest way to 0 meters per second. Starts the fastest and then stops.
Okay? Hold the thought.
What?
Hold that thought. Who voted B? Paige, Sydney, why did you vote B?
I voted B instead of the entire thing because throughout A you're slowing down.
This is true.
That's true, I guess.
I am slowing down on A. And what am I doing in B?
You're speeding up.
I'm speeding up.
That's fine.
So you voted B because you were associating acceleration only with speeding up. Yes. 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 And at this point you should go.
Yeah.
Now, what's the one word I do not, well, there's any number of words I do not allow in my classroom. What's one of them?
Deceleration.
Deceleration. Okay? So,
learned
the
something.
novice people that have never graced room G20 would say, oh, I'm decelerating and then I'm accelerating. Okay, here's my argument. when you look at force equals mass times acceleration, Newton's second law of motion, you will never see it as force equals mass times deceleration. Okay? It's always mass times acceleration. What does the slope of a velocity time graph always give you? Acceleration. Do I ever tell you, oh no, sometimes it's deceleration? No. The slope is always acceleration. So for those of you mostly that voted C, why did you vote C as the entire region? It's the steepest slope. Whether it's speeding up or slowing down doesn't make any difference. It does not make any difference. If I give you a velocity time graph and say, what's the maximum acceleration? Don't overthink this. Find the steepest portion of that graph. That is all you have to do. Okay, that's it. There is nothing else that you have to worry about. Now, is this acceleration making me speed up or slow down? Slow down. Why? I have positive with negative velocity. Okay? Now, visually, let's just make a visual estimate. I'm going to shift this back a little bit. Okay? So we get more like this. So, if I just gave you this velocity time graph and asked you, do you think you went further in the positive direction or further with a negative velocity? Which one would you say? Negative why? What'd you say, Riley?
Most of the graph is in the negative path.
Berkham's doing a funny day.
Huh?
What's going on?
What does the area represent?
Displacement.
Which area is bigger, the positive area or the negative area?
Negative area.
The negative area. So you can just look at the graph and go, that area is bigger than that area, which means that I went more in the negative. I spent more time in the negative displacement than I did in the positive. Now, I promise you, I'm going to ask you questions over that lab where it went in, hit the wall, and sprung back. So if you have anything wrong on that lab, okay, better make sure that you have it right. I promise you there's going to be questions on that lab. I promise you I'm going to give you questions involving the idea that distance traveled is velocity times time. If you get done at the end of this test and you have not used that equation, something has gone horribly wrong. Okay? So there are certain things that you have to have done when you hand in the test tomorrow. You have better have drawn a tangent line, you've better used your ruler and protractor, and you better have used this equation. Okay? I promise you, those are things that you have better, if you have not done any of those when you get done with the test, oh, something bad has happened. Okay? All right. Now, for the test tomorrow, you have everything back. Now, what I'm going to give you are two things. I'm going to give you, and I have to tell you how you use these. The first thing we're going to give you is a set of review questions for the test. This is not due, okay? You are not going to hand this in. If you want to do it, great. If you don't want to, that's cool. That's up to you. Now, I'm also going to give you the solutions to these problems, okay? So you can check that you did these. Now, this is how you don't do this or utilize this tool. Don't read number 1 and say, can a car change direction with constant velocity with uniform acceleration? And then read my answers and go, oh yeah, Bergkamp got that right. Okay, let's try number 2. Okay? Reading my answers and saying, oh yeah, Bergkamp got that right. God, he's just on a roll. Okay? No, that is not how you utilize this. If I were you, I would put this away in a hermetically sealed envelope and not even breathe on this thing until you get done with the review. Okay? Because otherwise you become biased, even on how you would solve the problem. I'm going to give you this. If you're serious about this test, I would put this away and not even look at it until you get to here. Now, this isn't everything that's going to be on the test, but it's going to be a vast majority of what's going to be on the test. If you can do this and feel very, very good about it, you'll be okay. Go back, look at all the assignments that you've given back. And I spend a lot of time grading your assignments. I correct them, okay? I just don't tell you, oh, what's wrong. I generally try and show you what went wrong or put something down on there. If you have missed anything on the assignments that you have back, figure out what went wrong. Now, at home tonight, just don't lay all your papers in front of you and mom and dad walk by. What are you doing? I'm studying, okay? You're not going to learn this by surrounding yourself with these papers, okay? It is an active engagement. Texting, checking your Facebook status, posting on Twitter, oh, studying for physics test. Everybody is going to laugh at you and go, no, you're not. You're an idiot. You cannot study and post to Twitter at the same time. No one cares anyway, okay? Cold hard reality. Oh, I've got 100 followers on Twitter. Okay, no. Do not put that down on your college application, all right? What's your major accomplishment? I hit 1,000 tweets in high school. No, okay? No one cares. I don't mean to burst your bubble, but no one really cares. They say they do, they don't. They're pathetic and don't have a life either. Okay, so study, 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 study. I'm done. Shut that off.